Namaste students. Welcome. In today's class, we're going to tackle a really important and I think a very fascinating topic from the F block elements. We're talking about the actinoids.
So, let me ask you a question. Have you ever wondered what actually makes nuclear power possible? I mean, what is the secret behind all that immense energy that a nuclear reactor releases? Well, the answer, it lies in a very special family of elements that we are going to study today.
Okay, so here's our plan for today. A quick roadmap. First, we'll do an introduction to these nuclear elements. Then, we'll see why they're like rebellious siblings in chemistry. After that, we'll uncover the secret of their 5F electrons, take a little tour of radioactivity, and finally, we'll see where these actinoids fit into our world.
All right, let's begin with our first section. So, the elements that hold the key to nuclear energy, well, they are called the actinoids. And believe me, they are a family with some very unique and very powerful characteristics.
So, what exactly are these actinoids? Simply put, they are a family of 15 elements, starting from thorium all the way to lawrentium. And if you look at the periodic table, you'll see they occupy that second row of the F block. Now, their very position, that itself is a big clue to their special nature.
But you might be asking, why is it so important for us to study them? Well, it's because these elements, they are right at the heart of nuclear chemistry. You see, if you want to understand big concepts like radioactivity or nuclear power or even nuclear weapons, you absolutely need a clear understanding of the actinoids. That's what makes this topic so relevant.
Okay, so to really understand the actinoids properly, it's very useful to compare them with their neighbors in the F block, the lanthanoids. This comparison is going to show us just how unique and different the actinoids truly are.
Here's a good way to think about the difference. Imagine the lanthanoids are like very well-behaved identical twins. Chemically, they are almost the same. But the actinoids, they are like the rebellious siblings in the family. Each one has its own distinct chemical personality, and each one breaks the rules in a different way. Thorium, for instance, is quite different from uranium, and uranium is very different from plutonium.
Let's get a bit more specific now. You see, the lanthanoids show a very uniform chemistry. They almost always form a +3 oxidation state, and generally, they are not radioactive. But the actinoids, it's a completely different story. They show all sorts of variable chemistry with many possible oxidation states, and, this is important, all of them are radioactive, a complete contrast. So the big question is, what is the reason for this huge difference? Well, it all comes down to a single, fundamental property that explains all this complex behavior of the actinoids. Let us now examine what that is. The entire answer, it lies in just one property, the shielding of their F electrons. This single factor, that's the master key to understanding everything about their behavior. Okay, here is the core reason, the main idea. In the lanthanoids, their 4F electrons are buried deep inside the atom. They're completely shielded, so they just can't participate in bonding. But in the actinoids, it's different. Their 5F electrons are less shielded. And what does that mean? It means they are more exposed, they are more available to actually participate in chemical bonding. I want you to think of it this way. The F electrons are in the basement of the atom, okay? For lanthanoids, that basement is completely sealed off, no entry. But for the actinoids, the basement door is open. The electrons inside can be accessed. And this accessible basement of electrons, that's exactly what leads to all those multiple oxidation states and their really complex chemistry. All right, so now we understand the secret of their electrons. Let's explore the consequences. I want you to imagine something with me. Imagine we are taking a walk, a tour, through a very special, restricted laboratory where these elements are handled. So we walk in, and the first container we see is for thorium. It looks quite stable, actually. Its chemistry is predictable. It mostly just prefers to be in a +4 oxidation state. You could say it's the most well-behaved of all the rebellious siblings. Okay, now we move to the next container. This one is holding uranium, and this is visibly different. You can see it's glowing faintly with radioactivity. Its chemistry is also more complex. It's like it has multiple personalities, easily forming both +4 and +6 oxidation states. You can see, the rebellion is growing stronger. And finally, we reach the last container on our tour. This one is for plutonium. Now, this element is intensely radioactive. It's the man-made troublemaker of the whole family. Its chemistry is extremely complex, showing a huge range of oxidation states all the way from +3 to +7. This little walk really illustrates how the complexity just increases as we move across the series.
Okay, so we've looked at the theory, and we have this mental image of the lab. Now, let's connect all this chemistry to things we can actually see and use in the real world.
You know, one of the most direct proofs of this variable chemistry is something you can literally see with your own eyes in the lab. If you take a solution of uranium V6, which is yellow-green, and you reduce it, it turns green because it has become uranium-4. If you reduce it even further, it turns pink as it becomes uranium-3. This beautiful color change, it is direct, visible evidence of those accessible 5F electrons doing their work.
And this chemistry, it has some incredibly important applications. Uranium, as we know, is the fuel for nuclear power plants. Plutonium is a key material for nuclear weapons, and other actinoids like americium actually have peaceful uses too. For example, it's used in the smoke detectors that we have in our homes. Now let's go back to that first question I asked you about nuclear power. You see, the whole process relies on uranium's complex chemistry. Specifically, it's uranium's ability to form a volatile gas, that's uranium hexafluoride, UF6, that makes the enrichment of nuclear fuel possible. Without this specific chemical property, it just wouldn't work. It's absolutely critical.
Okay, we've covered quite a lot in this short time, so let's just quickly recap the most important points that you should remember for your exam.
So, to summarize, point 1, actinoids are radioactive elements with very complex chemistry. Point 2, this is because their 5F electrons are less shielded, and this leads to variable oxidation states. And point 3, this special property is something we can see in uranium's color changes, and it's what enables huge technologies like nuclear power. Look, I know this can feel like a heavy topic, but trust me, if you just remember 3 things, the core idea of less shielded electrons, that mental picture of the rebellious siblings in the lab, and that one clear example of uranium's color change, this whole topic will feel much, much lighter for you. So I will leave you with one final thought to consider. We talked about plutonium, that man-made troublemaker. When you think about its immense power and its extreme chemical complexity, you have to ask, is plutonium the most remarkable or perhaps the most dangerous element that humanity has ever created? Something to think about.